for some amount of load. After that, there will be yield stress, and again, the stress started increasing with strain, but there is no relationship. So this particular state is called as plastic state. So once the material reaches plastic state, okay, the material will not get back to the original shape, and the deformation becomes permanent. So under plastic deformation, we cannot apply the material properties, equations. For example, we can't apply the Hooke's law. We can't. There's no meaning for Young's modulus, shear modulus, and rigidity modulus. So under plastic flow conditions, we need to apply a different set of conditions, so which we term them as the Levy-Mises equations. As you can see here, the Levy-Mises equations. Okay, so these are the Levy-Mises equations. So Levy-Mises equations actually relates the stress-strain relationships in terms of effective stress sigma dash. Effective stress is the sigma dash. Then effective strain is epsilon dash. So in terms of effective stress and effective strain, and here it is incremental increase in the strain value. So d epsilon 1 is the incremental increase in the strain value. So it is related to the stresses in the 3 dimensions. So using the Levy-Mises equations and calculating the effective stress and effective strain, then we'll be able to apply the Levy-Mises equations under plastic flow conditions. So we have seen the elastic stress-strain relationships in under elastic deformation, and we have studied about the safe field, about von Mises equations relationship and Tresca relationship. And under plastic flow conditions, we have the Levy-Mises equations. So we have seen the application of Levy-Mises equation in a couple of problems we have discussed in the last session. So now we have to do one more problem. So let us go through that problem first. So this is the last problem under plastic flow conditions. Guys, can you see this? The slides are visible to you? All right, I presume you can see clearly the slides. All right. Okay, Shashwindra. So here we are discussing with a geometry, which is a plate. Okay. So here the plate is of mild steel and the dimensions of the plate are given. So the initial dimensions of the plate are, so thickness is 10 meters and the length is 1000 meters and the width is 500 meters. So this is stretched plastically 25% in the longitudinal direction. So this amount of stress in the longitudinal direction is 25%. So guys, can you tell me what will be the final length of the plate? So what will be the final length of the plate? Heva, I think you want me to record? Okay. I'll be recording the session, but slowly I want to, okay, stop recording the sessions. Okay. Can you guys tell me what will be the final length when the plate is stretched plastically by 25%? So here the stress is plastically, that means the material is undergoing plastic deformation. So what will be the final length? So the initial length is 1000 mm long. That's correct, Dicheng. So the final length will be 1250 mm. Okay. The width, the initial width is given 500 mm and thickness is 10 mm. Okay, the stress-strain relationship, because the material is undergoing plastic deformation, so the stress-strain relationship will be given as part of the material property here. So the effective stress is 500 times the strain to the power of 0.4 megapascals. Now you are asked to assume the width is restrained from contracting by lateral end grip. So there's no change in the width. Okay, so the width is restrained, only the plate changes in terms of length. Okay, so in such a scenario, so find the final dimensions of the plate. So you know that the final length is 1250. So the dimension, the width is the same. So what will be the thickness? So what will be the final thickness? Guys, you got the question? So try to work on the final uh, thickness, the final dimensions of the plate. So including the final length, final width, and the final thickness. So you are dealing with a plate. Okay, so the initial length is given 1000 meters. Okay, the plate is stretched in the longitudinal direction. So the stretch is by 25% and it is plastically. Okay, width is restrained. So the initial width is, okay, how much it is given? 500 meters, 500 mm, sorry. So the units are in mm. Okay. So the initial width is 500 mm. Okay. Then the initial thickness is given as, so you can just write thickness 10 mm. Okay, so this is all the given data. So you're asked to find out the final dimensions. So what are the final dimensions? Okay, so since the plate is having 25% of stretch and plastically, so the final width will be, so the final length. So will be 1250 mm because it is 25%. So for 1000 it will be plus 250 mm. The width is restrained, so the final width will be remain same. So that is 500 mm. So now you need to calculate the final thickness. So final thickness. So guys, can you calculate and tell me? So basically the total volume of the material will be constant. So we can say that the initial volume is final volume. So initial volume of the plate is equivalent to the final volume. So please calculate and let me know. I'll be waiting for your answer. Any answer, guys? That's correct, Henry. So we need to compare the volume of the plate initially and finally equate. Okay, so you can say that the length initial multiplied by the width initial multiplied by the thickness initial is equal to the length final multiplied by the width final multiplied by the thickness final. So if you do this, 1000 plus multiplied by 500 multiplied by 10 is equal to, so this will be 1250 multiplied by 500, so multiplied by the final thickness. So from this you can see that the final thickness will be 8 mm. All right, so this is the calculation for the final thickness. After that, then we need to calculate. So we need to calculate part B. So part B refers to the state of the stress at the end of the stretching process. So state of the stress at the ending process means you need to calculate the uh, uh, the total stress at the end of the stretching process. So to calculate the part B, okay, so we know the stress strain relationship is given as 500 into strain to the power of 0.4. Okay, so for doing this, you need to calculate the, we have done this part A, part B. So calculate what is the strain in the longitudinal direction. So what will be the strain in the, okay. So calculate and let me know what are these things. So what is the strain in the longitudinal direction? Just calculate. So strain in the width, then strain in the thickness. Okay. So guys, let me know what are the values for this. So any answer for the first one? The longitudinal strain 0.223 is correct. So you can say 0.223. So what about the strain? So any unit for this? Let's start reaching. So this is 0. Then the strain in the thickness. Yeah, that's correct. No units. Shafruddin, that's correct. All right. So what about the strain in the thickness?
Introducing Grammarly.
Yeah, because the total strain should be 0 because the volume is constant. So it will be negative 0.223. Okay. So now to calculate the stress, so we need to at the end of the process, so you need to calculate the effective strain first. So we know the three components of strain. So now we calculate the effective strain. So to calculate the effective strain, so we apply the formula square root of 2 by 3 epsilon. We can also refer these things as 1 and 2 and 3, epsilon 1, epsilon 2, and epsilon 3. Okay, so you can apply the effective strain expression. So square root of 2 over 3 into uh, epsilon L minus epsilon W, that is width whole square, plus epsilon 2 minus epsilon 1, 3 whole square, plus epsilon 3 minus epsilon 1 whole square, the entire thing under square root. So do calculate and let me know how much your answer. So please let me know. So you know we can write epsilon L minus epsilon W is 0. So 0.223 whole square, then this is 0 minus epsilon T. So there's a square missing in the formula, so please add. So 0.223 whole square, then epsilon T minus epsilon L. So minus of minus, this becomes positive, so it will be 0.44 square. So calculate and let me know your final answer. That will be your effective strain. I'm waiting for your answer, guys. So it is 0.2575. I think that appears to be all right. So you can write this as, thank you, Safruddin. So 0.2575. I hope others also got the same answer. So once you know the effective strain, then you can calculate the final stretching load. Okay. Uh, and, this is only the effective strain. So now you know the stress strain relationships, right? So you know the stress strain relationships. Now you can write a stress at the end of deformation process. So you can write this as sigma is equal to 500, then effective strain to the power of 0.4. So you can write 0.2575. So 0.2575 to the power of 0.4. So can you calculate the effective stress, guys? So please calculate the stress at the end of the deformation process from the given stress strain relationships. So for the plastic deformation. So any answer here, let me know. 290.6 watt units. Uh, unit, no, megapascal. That's correct, Dicheng. So because whatever the units, this expression tells you that the stress strain relationships are given in megapascals. So therefore, whatever the answer you get, 290.6 will be in megapascals. And guys, let me tell you at this point of time, I was going through your mechanical vibration assignments, and consistently a good number of students, they ignored writing units for stiffness constant or the damping constant or the natural frequencies or the natural frequencies. So wherever you miss writing the units, I would like to remind you that you may be losing some marks, So though a minor percentage of marks you will be losing, so it is always necessary for you to write a unit for whatever the numbers you are giving, of course, except strain. All right, so this is the stress at the end of the deformation process. Now, after that, let us see the third question. The third question asks you, so what is the final stretching load? The final stretching load. So that means you need to calculate what is the force acting on this. So what is the force acting on the plate? So when the plate is stretched 25% plastically. So we know the effective strain, we know the stress at the end of the process. So therefore, you should be able to calculate the uh, final stretching load. So the final stretching load, I'll just leave it to you to calculate. You can use the formula. Force, basically the stress is force over the area acting. All right, so I leave this to you, and you can include this. Then, okay, you can know area of the plate. Then you know the stress. So therefore, you can easily calculate the force acting on the plate or the final stretching load at the end of the deformation. All right. Okay, after this, then we move on to the next topic. So the next topic is about elastoplastic bending. So that means when the material is not fully plastic, okay, not fully elastic. So it is undergoing both, a part of the material is under elastic deformation and a part of the material is under plastic deformation. So this is a state where the material is partly in plastic and partly in elastic bending. So part of the material under elastic deformation, the part of the material is under plastic deformation. So that means the plastic bending is not complete, the entire material. So let us see what happens under elastic plastic conditions. Okay, so this is the stress strain relationships which we have seen. Okay, all this material I have taken from the learning guide. Okay, uh, okay, so this is basically the stress strain relationships for a metallic material. So we know the yield stress. Okay, After that, okay, the plastic region. So during this state, elastic condition, so the stress is proportional to strain. So here this YP denotes the yield point of the material. So at which, so the material is fully transforming from uh, elastic deformation to plastic deformation. So corresponding to the yield point, so epsilon YP represents the strain corresponding to the stress. All right, so we move on to the next slide. Uh, you may just go through this description here. So you pay attention here. So what is happening is, so when the load is acting on the material, so you can see the material deforms from the upper fibers of the material. So from the top fibers and from the bottom fibers of the material. So in this particular figure, you can see part of the material at the top and bottom. So this is your neutral axis. Okay, so this is your neutral axis. So with respect to the neutral axis, okay, the deformation starts from the outer fibers, okay, above and below. So, if the deformation above the neutral axis is uh, okay, here you can see it is elongation. So here it is, okay, it is a stress. Okay, so part of the material at the top and bottom are under fully plastic deformation. And you can see, okay, so this portion of the region is still under elastic condition. So here, this is elastic condition. So under this particular state, you can see part of the material at the outer fibers and at the bottom fibers is fully plastic, and it is closer to the neutral axis at the top and bottom. The material is still elastic. So this is a partly elastic and partly plastic condition. Now, as the load keeps on increasing, so the plastic yielding uh, from the top and from the bottom reaches the neutral axis. So now this is the state where the material is fully plastic. So the material is fully plastic. So under fully plastic conditions, okay, so the problem is how to locate the neutral axis. So generally we identify the neutral axis, okay, by applying the equation for the area. So what we do is, if you recall the solid mechanics too, so we have estimated the neutral axis y bar as sigma y bar dash a dash, okay, a over sigma a. So the total area. So y bar dash is the neutral axis location of the centroid for the individual rectangle. So the cross section may consist of number of rectangles. Okay, so this is how we can locate the neutral axis under elastic conditions by applying the areas formula. Okay, so but when the material is under fully plastic conditions, we cannot apply this formula. So in the limiting case of fully plastic action, the neutral axis assumes a position such that the total cross-sectional area is divided into two equal parts. So now under fully plastic conditions, now how to find out the neutral axis, how to establish the neutral axis. So you can see here under elastic bending conditions, I'll go back. We have discussed the elastic flow conditions. Now let us see the plastic flow conditions. So under the fully plastic flow conditions, we'll be applying under the equilibrium. So integration sigma dA is equal to 0. Okay. So that means we need to apply this formula. So we need to divide the cross section into areas of compression and areas of tension, and then we apply the integration of the total resultant force acting on the system. So this is sigma into dA is nothing but the total resultant force acting on the system. Force is nothing but stress into area, right? So we apply this expression, that means integration of sigma into dA, to find out the neutral axis. So this part we can understand better by going through some examples. So in this particular slide, what we see is how elastic plastic bending is taking place. Okay. So in the first scenario, this is fully elastic. The material is fully elastic. Okay. So here, this is partly elastic, partly plastic, and partly elastic. And here there's more plastic and less elastic. So this is completely, the system is under fully plastic conditions. All right. So now let us look at this question. This is a beam is shown below and is made of an elastic plastic material, for which the yield stress is given for this material as 360 megapascals. So you're asked to find the plastic moment and the maximum elastic moment, ME. So the plastic moment refers to the movement acting under plastic conditions. So elastic movement is the movement under elastic conditions. So we need to find out both plastic movement and elastic movement. So we know that movement we can apply the Fleischer formula to calculate the moments. And you're also asked to determine the distribution of the residual stresses. So residual stresses means when the movement is applied and removed, so there will be still some amount of stress is left within the cross section. So that is the residual stress. Okay. After the plastic movement, and the plastic movement is applied and then released. So that will be the residual stresses. So we know the cross section, the dimensions of the cross sections are given. Okay, so we know all the required dimensions of the cross section. And we know that this particular material will have elastic. Okay, the yield stress is given as 360 megapascals. So now to calculate the elastic movement and plastic movement acting on this cross section, so what we need to do is first we identify the material under zones of tension and zones of compression. So now the same material is shown here. Okay. So what we are doing is we are identifying, we choose hypothetically some neutral axis. So we consider, let us say this is the neutral axis. So now we have to establish this neutral axis when the material is fully plastic. Okay, so to do this, now we can consider this zone as compressive zone. Okay, and below the neutral axis, so we can consider the areas as under tension. So we can divide the entire cross section into two zones of compression, C1 and C2. And for calculation ease, so we can consider the zones of tension below the neutral axis. So we have T1 and T2 and T3. Okay, so now from the base, from the bottom, so the height D we need to find out. So this is what is the establishing the neutral axis of on the cross section when the material undergoes fully plastic deformation. Okay, so we choose hypothetically some neutral axis. Above the neutral axis, we are choosing the zones of compression. So we call them as C1 and C2. And below the neutral axis, so we have the tensions. Okay, and these zones we can, for calculation purpose, we can call them as C1, C2, and the zones of tension as T1, T2, and T3. So we need to find out this D, which is the height from the base of the cross section to the neutral axis. So that means, so we'll be able to establish the neutral axis once we know, or once we estimate this D. Okay, so to do this, so we can apply the area integral. So sigma into dA is equal to 0. So that means under fully plastic conditions, the resultant force acting on the cross section will be 0. So that means integration sigma into dA is equal to 0. Okay. So now to do this, we need to calculate the areas of tension and areas of compression. Okay. So you can consider T1 as, okay. So the plastic yield stress is given. So we can write this as sigma Y. So the tension acting. So tension is sigma into the area. So what will be the area here for C1? So this one is the total height of the cross section is 200. So what will be this height? So how much you can write, guys, here? Sigma Y multiplied by, so this is 40 mm. 200 minus D into 40. Let me check what are the dimensions. Yeah, this is given as 200. Then you can similarly write, so you can see that T1 is equal to T2, right? So based on the dimensions given, so you can write T1 is equal to T2. Uh, T1 cannot be 40 into, T1 is only this. Dicheng, I think you need to change your equation. So this will be sigma Y into, so 40 mm, you can write 40 mm thickness. But what will be this height? I'm sorry, I think I shown wrongly for C1. Instead of C1, we are writing for T1, right? So for T1 is only this height. How much you can write? Yeah, so sigma Y into 40 mm into, or D minus 40. Okay, so this is T1 and T2. What about T3? So can you write similarly T3 value? So T3 is the tension under the entire this block. Okay, so T3 can be written as, so sigma Y, the yield stress is 360 megapascals, which is given. So we can write Uh, so I just write sigma y because we know sigma y. Then the area of this block. So area of this block will be, so 40 multiplied by, so what will be the total width? So that is 225 plus 80. So 40 this side, 40 this side. So the total is 305 mm. So this will be T3. Okay. So now write down what are the values for C1 and C2. So C1 will be, and the compressive zone at the above the neutral axis. So C1 will be sigma y into the area of this block. So the area of this block. So what will be the area of this block? So we can write 40 mm multiplied by, okay. So the total height of the block is given 200. So you need to take out this d. So here we can write 200 minus d. Okay. So C2 is the same as C1. Okay. So we can imagine the neutral axis on the section. Now, with respect to the neutral axis, then we can identify the zones of compression and zones of tension. So then we write the tension acting in the above the neutral axis, and the compression acting above the neutral axis and the tension acting below the neutral axis. And the expression says the sum of sigma into dA is equal to 0. So that means the total force acting on the system on the cross section will be 0. So that means T1 plus T2, so plus T3 minus C1 minus C2 will be 0. So this is the total resultant force acting on the cross section. So if you apply this equation and solve, then you'll be able to, the only unknown is the D. Okay, you'll be able to calculate the D. Guys, any questions on this? Let me know. So first we need to write the T1, T2, then T3, then we write C1, C2, okay? And in this case, T1, T2 are same and C1, C2 are same. So therefore, to calculate the resultant force acting on the cross section 0, so we can add the stresses and subtract the, we can add the tension forces and the compressive forces we can subtract. So the net force acting on the cross section will be 0. So once you apply this equation, then you will be able to find out the neutral axis, the height of the neutral axis, d. Guys, take some time and calculate. Okay, so I'll show you here. Okay, so this is what we are doing. So tension 1 is tension 2, so tension 3. So sigma y is replaced with 360 megapascals. Okay, so since it is 40 mm, so 40 into 10 power minus 3. Okay, so this is, so you are converting mm into meters. Okay, so T3 sigma y into 305 into 40, so you can just calculate as it is. Okay, so then C1, C2, we are calculating C1, C2. So here, D is unknown. So also you can see D here unknown. So now the net resultant force acting on the cross section is 0. So we can write T1 plus T2 plus T3 minus C1 minus C2 is equal to 0. So once you calculate T1, T2, then C1, C2, okay, and C3 is calculated, and find out the value of D. Any answer for D, guys? I think I'll move to the camera, so that will be easy. So uh, we write T1 plus T2 plus T3 minus C1 minus C2 is equal to 0. Okay, so substitute. So substituting a T1, T2, T3, and C1 and C2 values. Okay, find D. Okay, so guys, I'll give you 5 minutes, calculate. And afterwards, you need to calculate what is T1, what is T2, what is T3. Then calculate C1 and C2. First, establish the neutral axis D from the bottom. So let me know the moment you get the D value. I think that's correct, Michael. So you will be getting about 43.75 mm. So the D value will be 43.75 mm. So that means, so this is the neutral axis of the cross section from the bottom. So when the material is, when the entire cross section is fully plastic conditions. Okay. So under fully plastic conditions, now you can calculate what is the tensional force T1, T2, T3. Okay. So you can calculate what is T1 and T2. So you, once you know D, you also know T1 is equal to T2 is equal to sigma y, which is 360 megapascals, into 43.75 minus 40 mm. So into 40 mm. So once you calculate this, how much you get, anyone? So first calculate T1, T2. So guys, any answer for T1 and T2? 54 kilonewtons. Okay, that is correct. So, but we prefer to write in meganewtons. So you can write 0.054 into 10 power 6 newtons. Okay, so T1, T2 will be 54 kilonewtons or 0.05 into 10 power 6 newtons. What about T3? Michael, that's correct. So P3 will be 360 megapascals multiplied by 40 mm, 305 mm. Yeah, that's correct. So we can write as P3 is equal to 4.392 10 power 6 newtons. So similarly calculate C1 at C2. So this will be so let me know C1, C2. 2.25 into 10 power 6 newtons. That's correct, Heva. So we can write 2.25 into 10 power 6 newtons. So 2.25 into 10 power 6 newtons. So now we need to calculate the plastic moment. So we know that the moment is nothing but the force multiplied by the perpendicular distance acting on the system. So here our system is something like this. So we have, I just draw this again, just for, okay, let us say the system is like this, the structure, the cross section, and let us say this is our neutral axis. So this is our neutral axis. So these two are the tensions. So this is your T1, this is your T2, this is your T3, this is your C1, C2. Okay. So to calculate the plastic moment, we know tension T1. Okay. So you need to multiply this from the centroid of this zone, okay, to the neutral axis, from the neutral axis. So you know the height of this is, okay, so you know it is 3.75, right? So you know this is 40. So this is 43.75. So this will be 3.75. So we need to take half of this 3.75 mm. Okay, so how much will be 3.75 mm over 2? So we need to multiply T1 multiplied by the perpendicular distance from the neutral axis to the centroid of this tensional zone. So similarly from the T2. So both the distances will be the same. Okay, we know T1, T2 are the same. So we need to multiply with the height of this block over 2. So that will give you T1 into 1.875 mm plus T2, you need to multiply again with 1.875, then plus T3. So for T3, so we need to calculate from the centroid to, from the neutral axis to the centroid of this zone. So if you consider this is all T3, so to the center of the T3 zone. So this is 40, so half of that will be 20 plus 3.75. So you are multiplying T3 with 23.75. Okay, so then plus C1 multiplied by, so from neutral axis, we need to take to the centroid of this. So this will be, okay, so what will be this height? So this is 200 minus 43.75. So 200 minus 43.75 is, so this will be 156.25 over 2. Okay, so you're multiplying C1 with 165.25 over 2. So that will be 78.125. So plus C2 into 78.125. So now use the proper units, okay? Then do this multiplication and sum up all the things that will give you the plastic moment MP. Guys, is that clear? Any questions? Let me know. So I separate out this. Okay, so the calculation is T1 multiplied by this distance from the neutral axis to the center of the T1 zone. Then plus T2 multiplied by the same distance. Then plus T3 multiplied by the neutral axis to the center of this T3 zone. So plus C1 multiplied by from the neutral axis to the center of C1. So similarly, plus C2 multiplied by the distance to the center. Guys, any questions, let me know. Otherwise, I'll leave this to you for calculation purpose. Where is the 3.75? Okay, so 3.75 is because, you know, this is the total, this height is 43.75, right? This is your D. Okay, so that means this is 40. So this will be 3.75. The whole thing will be 3.75. So this will be 3.75. So simply 43.75 minus 40. Is that clear, Heba? Why? Because you are looking to the centroid of this zone. So from neutral axis to the center of this zone. So that's why everywhere we have to divide with the 2. So movement is nothing but force multiplied by the perpendicular to the zone. But here we consider that the entire system as one point mass. Okay, so the point mass means at the centroid of the geometric figure. So therefore, we need to multiply from neutral axis to the centroid of that to get the plastic moment. Because when the cross section is fully plastic condition, we establish the neutral axis. And we know there are forces acting in the different parts of the cross section. Now, to get the plastic moment, we need to multiply the force with perpendicular distance, appropriate perpendicular distances. Now, these perpendicular distances are nothing but the half of the height of the zones. Is that clear, Heva? All right. So calculate, then you will get plastic moment. So I'll leave it to you for calculation purposes. So after that, then we need to calculate the elastic moment. So after plastic moment, elastic moment. So elastic moment, we can write it as my, or we can write it as me. Okay, so we just write it as me. So we can write this as, so the yield stress, plastic yield stress multiplied by inertia through the neutral axis from Flexner's formula over the C. Okay, so we know, if you recall from solid mechanics 2, from the Flexner's formula, so the maximum stress acting on a cross section is mc over inertia through the neutral axis. So this is the formula. So here the moment is the elastic moment. Okay, so now we are estimating elastic moment. So we can write elastic moment as the yield stress multiplied by the inertia through the neutral axis over C. Now, when you want to calculate this moment of inertia, elastic moment, okay, so you need to calculate this inertia through the neutral axis. So inertia through the neutral axis. Now we apply the uh, because all our cross sections are rectangles, so we apply the formula for the rectangle and with parallel axis theorem. So we can write 1 over 12 BH cube plus A D square. So this is the inertia through the neutral axis for calculating elastic moment. Okay, so you can apply this formula, then calculate inertia through the neutral axis. So once you know inertia through the neutral axis, then the yield stress is given 360 megapascals. Then you can find out C. So what is the C? So C is the distance from neutral axis. So NA is the neutral axis to the farthest point on the cross section. To the farthest point on the cross section. So that C in this scenario is, if you see our neutral axis to the farthest point will be from neutral axis to the top of the uh, cross section, which will be 156.25 mm. Okay, so this is from neutral axis to the farthest point means you need to go all the way to the outer fiber. So this distance will be 156.25. So because the total is 200, so 200 minus D, which is 43.75. All right, so you know the C, then you need to calculate inertia through the neutral axis. So this we have done in your solid mechanics 2 course. So you just apply this formula, then you'll be able to calculate inertia through the neutral axis. So once you know, then you will be able to calculate the elastic moment, sorry, ME. Okay, so sigma y given. C in this case is 156.25. So inertia through the neutral axis, so you can apply the areas formula, okay, uh, applying the parallel axis theorem. So because we are dealing with rectangles, so we can apply the inertia for the rectangles because it's basically a geometric property. All right, so then you will be able to calculate elastic moment. I just write the formula. So inertia through the neutral axis over C. So once you calculate elastic moment and plastic moment, okay, always the plastic moment will be higher than elastic moment. So if your calculation will yield you more than plastic movement, that means your calculation is incorrect. So plastic movement will be always greater than elastic movement. So once you calculate both the things, then you can calculate the residual stresses. So residual stress is, okay, so this you can calculate under two categories, the residual stress at the top. Okay, so here to calculate this, we use the plastic movement into C over inertia through the neutral axis. Then you can calculate the residual stress at the bottom. So here we can write MP into C, the same formula, inertia through the neutral axis. So when you're calculating the residual stress at the bottom, so the C value will be 43.75 mm. So when you are calculating for the top with respect to the neutral axis, so here the value will be 156.25 mm. Okay, so you will be able to calculate the residual stress at the top and bottom. Guys, any questions? Let me know. Noor Azhar is asking 23.75. Where is the 23.75? The previous paper. Let me check. So where is 23.75 Azhar? Oh, T3 distance. Okay. So T3 distance is only okay 43.75 over 2. Did I write this 23.75 here? Sorry. So this is 43.75, right? So 43.75 over 2. So it is not 43.75 over 2, but it should be, this one is 3.75, right? Then to the center, so 20, yeah. So you will get 40 over 2 plus 3.75. So that is this correct, Heva and Michael. Is that clear, Nurozak? So from where you are getting this 23.75? All right. So I'll leave the calculation part to you. Okay. Uh, Once you calculate the residual stress at the top, so you'll be using for the top, okay, 156.25, and for the bottom, 43.75. After that, then I'll go back to the slides. Okay, guys, pay attention here. So uh, you will have some help to check your calculation. So you calculate the residual stress at the top and residual stress at the bottom. Okay, so once you know the residual stress at the top and the bottom, so this is the cross section you can imagine. Okay, so this is the cross section. So we are considering the top is compression. Okay, you can see the direction of the arrows here. So these arrows are okay. So you can see the arrows, they indicate compression with respect to the neutral axis. So with respect to neutral axis, the bottom is 43.75 mm. So the top of the cross section is 156.25 mm. So you need to plot this residual stress distribution. So you know that the plastic yield stress acting is 360 megapascals. So now with respect to the neutral axis, so this is your neutral axis, and the dotted line, the red dotted line is the neutral axis. Okay, so the red dotted line is the neutral axis. So with respect to the neutral axis, so this is the compression I just indicate as C. So this is under tension. Okay. So when the plastic stress is applied and released, so the residual stress at the top you can calculate from here. Okay, so whatever the value you get at the top you can calculate, and at the bottom you can calculate. Okay, so just to guide you, I think you will be getting about 6.6 megapascals at the top here. And at the bottom, you will be getting about 181. Okay. One 8.1 or 18.06 megapascals. Okay, so the top will be 646.6 and the bottom will be about 181 point. So you can indicate from 646.6, okay, it goes to 0 point at the neutral axis, then it goes to the bottom 181.1 megapascal. So this stress distribution plus, okay, the residual stress, when you leave this, so the amount of stress, residual stress distributed on the cross section, you can write like this. So this is 360. You can look at the arrows here. Okay, so this is the residual stress at the top will be tensional stress. So you need to subtract 360 minus 646. Okay, so you actually this is minus 360 plus 646.6. So that will give you roughly 286.6 megapascals. So this is the residual stress left at the top. So similarly at the bottom, so you can write here it is 300 positive megapascals. Okay, so when you add plus here this is negative, so here this is negative. So at the bottom 300 minus 181.1, so that will give you about the residual stress here as 178.9 megapascals. Okay, so you can see the stress at the top is positive, the stress at the bottom is also positive. So that means at the neutral axis here, the applied stress will be 300 megapascals. Okay, so that means from 286 megapascals, the residual stress becomes 0, and then it becomes negative 300 here, and again it becomes positive 178.9 here. Okay, so this is the residual stress left within the cross section. Clear? Okay, so in simple terms, so you write down the values here, write down the values here. So look for the arrows, okay, the tension and compression. Okay, so this is compression and this is tension. So this is the stress left out. So we need to calculate this Y. So what is this Y? So the Y represents the zero stress acting on the cross section from neutral axis. So with respect to the neutral axis, so at what height within the cross section, so there is a zero stress. So this is the zero stress point. So that you can calculate at what height the zero stress is acting from this analysis. So it's from area of triangles, so you can apply. So you need to show this stress distribution and provide some description of this in the assignment. Guys, any questions? Otherwise, I'll think we're done this question completely. So definitely there will be a question in the end of term exams about this, and it will take a substantial amount of time to calculate both the plastic moment and elastic moment. The good thing is the procedure is exactly the same. Okay, so to calculate plastic moment, you need to establish the neutral axis first. Okay, so to establish the neutral axis, then we'll apply the sum of the resultant force acting on the cross section 0. So we assume a neutral axis. Okay, so with respect to neutral axis, so we identify the zones of tension and compression. Then we say that the total resultant force acting on the cross section is 0. So we'll apply this relationship. So from there, there will be only one unknown, so you will be able to calculate that unknown. Okay, so that means you'll be able to establish this y dash, or sometimes we call y dash, or sometimes we call this as d. Okay, so basically you are establishing the neutral axis under plastic conditions. So you know d. So once you know d, then you can identify or you can calculate the forces, tensional forces and compressive forces acting on the cross section. So once you know, then you can actually know the amount of forces. So you know the T1, T2 values, the C1, C2 value, and of course the T3 value also. So once you know, once you calculate T1, T2, T3, C1, C2 values, then you can calculate the plastic moment based on the our definition. Sorry. So then you can calculate the plastic moment. So when you calculate the plastic moment, so for each zone, what is the force? Okay, for example, this is C1, right? We called it as C1. So that is C1 represents the entire force acting on this area. So multiplied by the distance from the neutral axis to the centroid of this rectangle. Okay, so that gives you both C1 and C2 will be the same. So that gives you, yeah, I think I have shown you when I use the camera. Okay, half of the distance, I think 156.25 over 2. Okay, so you can calculate the plastic moment. So once you know plastic moment, then you need to calculate the elastic moment. So to calculate the elastic moment, so you need to find out inertia through the neutral axis. So once you know inertia through the neutral axis, so here you are calculating the inertia through neutral axis by using the standard method. Okay, so once you know, then you will be able to calculate the elastic moment. So elastic moment will be, so the yield stress given multiplied by the inertia through the neutral axis over C. So C is defined, okay, as the distance from the neutral axis, the maximum distance from the neutral axis. So if you are calculating the total elastic moment acting on the cross section, so the maximum distance will take it as 156.25 mm. But we can calculate the residual stresses at the top and bottom. Okay, so we use the plastic moment and C. So for the top means, so the C will be 156.25. So from the neutral axis to the top of the cross section. Then the residual stress at the bottom will be from the neutral axis to the bottom of the cross section. So for the bottom, the C value will be 43.75. So you need to know this, you need to apply this distance. Okay, after that, once you calculate the residual stress at the top and bottom, then the stress distribution will be So this is the yield. Okay, so this is the plastic yield stress. Then this is the residual stress at the top and residual stress at the bottom. So the plastic yield stress plus the residual stress at the top and bottom will give you the residual stress distribution on the cross section. So based on the numerical values, so you will be able to draw approximately how the stress distribution looks. So you need to focus on the direction of the arrows. All right. So then you'll be able to establish and at what height the residual stress will be zero on this cross section. So okay, that is your Y. All right. Guys, before I move on to the next question, any doubts, let me know. So do you have any questions or any doubts? Let me know. Yes, 100% you need to draw this. So, yeah, for the assignment, yes. For the exam, depending on the question. If the question asks you to draw the stress distribution, okay, then you need to write. So if the question asks you to draw the stress distributions, then you need to draw this. All right. So any other questions? All right. So if you have no other questions, then we have slightly a simple question. The question two will be slightly simpler. So you need to work on this. So the dimensions are all given on the cross section. So all the dimensions are given. Okay. So you need to identify the neutral axis approximately. Then you need to, for plastic movement, calculate the height from the neutral axis. Let me check. Okay, so you can take the cross section as given. Okay, so then first calculate what is the neutral axis for this. Inertia through the neutral axis. So we can, because this is a perfect geometric figure, so you can choose the neutral axis at the exactly at the center. So the dimensions are the same. So this you can call as your neutral axis. So with respect to the neutral axis, then you calculate inertia through the neutral axis. So here 1 over 12 bh cubed, so 1 over 12. So B, you can take the bottom rectangle, okay? So the bottom rectangle. So 200 mm, that is 0.2. H is 15 mm, so that is 0.015. So 1 over 12 bh cubed. So the top rectangle and the bottom rectangle are both the same. So you can just multiply with 2 here. Okay. So 2 into 1 over 12 bh cubed plus AD square. We need to apply AD square because we know this formula is applicable only for the rectangle. So, but the neutral axis for the entire composite body is away from the neutral axis. So the neutral axis for this will be somewhere at this point. So you can probably draw the neutral axis for this rectangle here like this. Okay. But since the composite body, the neutral axis is away, so now you should know the distance from sorry. So you should know that this distance. Okay. So AD square, so area is for the rectangle 0.2 into 0.015. 200 mm is 0.2. So 15 mm is 0.015. So you will get the area of the rectangle A. Now D is the distance from the centroid of the axis to this neutral axis. Okay. So this height is 200. So that means this height will be 100. So this will be 100 mm. And the neutral axis for this would be 15/2. So that means this height is 7.5. So therefore, from the neutral axis to the centroid of the top and bottom rectangles will be 107.5. So this is the so-called D here. Okay, so this D represents the neutral axis of the bottom rectangle to the neutral axis of the composite body, so the distance. All right. So once you do this, then you will get for the top and bottom rectangles. Okay. So for the top and bottom rectangles. So now for the center rectangle. So for the central rectangle, okay, there is no need to apply the AD square. Why? Because for the central rectangle is a perfect rectangle. So the centroid for this rectangle okay, I'll just use this. So you can see the centroid for this is the same as the centroid for the composite body. So the neutral axis will be the same for the center. Okay, the middle rectangle. So that means the D value for the middle rectangle will be 0. So only 1/12 BH cubed you need to do. So 1/12 B is the so the height is given 200. Okay, so the base is given as 20 mm, I think. So if you see the dimensions here, so here it is given as 20 mm, the dimension. Okay, so the thickness of the middle rectangle is given as, the width is given as 20 mm. So you can write as 0.02 meters. Okay, the height is 200 mm, that is 0.2 meters. So if you do this calculation, then you will get inertia through the neutral axis with the given cross section. Okay, so then you can calculate the uh, elastic elastic moment. So sigma y into inertia through the neutral axis over c. So what is c? C is the distance from neutral axis to the farthest point on the cross section. So if you consider the so neutral axis is somewhere at the center. Okay, the farthest point is the same to the top and bottom because this is a perfect geometric shape. So C will be 230/2. That gives you 115. Okay, C is the distance from neutral axis to the farthest point on the cross section. So this is a perfect symmetric body. So the farthest point distance is the same to the top and bottom. So which is 115 mm. Okay, so you can use this and you can calculate the elastic movement. Okay, so the plastic movement again as the plastic movement you can calculate. Okay, so you can apply the same thing. Okay, you can identify the zones of tension and compression for that. So I'll just show you the figure. So if you take okay, let us say your figure is something like this. So it's a perfect figure. So, okay. So you need to identify the zones of tension and compression. So you can consider this is your C1. So you can consider this is your C2. Okay, actually, let me just draw a neutral axis. So imagine a neutral axis like this. Okay, this is your neutral axis. So with respect to the neutral axis, you can choose this as your C1. Okay, so this one will be your T1 and this one will be your T2. Okay, so write down again the sum of the compressions and tensions will be 0. Then you will be able to find out the neutral axis. Then you apply the momentum formula for plastic moment. Okay, so then you can calculate the plastic moment. So once you get the plastic moment, then you can uh, calculate the residual stress at the top and bottom. So in this case, this is a perfect geometric figure. Therefore, the residual stress at the top and bottom will be the same. So you will get the residual stress at the top and bottom will be the same. Okay, so the stress distribution looks something like this. Okay, so you guys can work on this problem neatly, and when you do your assignment, everything should be done step by step in a clear and neatly, and you need to demonstrate that you clearly understood the problem. All right, any questions, guys? The good thing is that the bad thing is the calculations are long and okay, bit tough. But the good thing is the procedure is systematic. So you have the same way you calculate establish the neutral axis, calculate the inertia through the neutral axis, then apply the formulas for plastic movement and elastic movement, then apply the same formulas for residual stress at the top and bottom. So then you draw how the residual stress distribution left within the cross section. So after the plastic release, Daryl, I think this is the paper I'm telling you from the beginning itself. Okay, the question paper, there will be 6 or 7 questions. Okay, and you will have 3 hours time. This is the same for on-campus, off-campus students for the last 20 years. So the time is 3 hours only. 15 minutes will be the reading time. And I think that includes your scanning and uploading the documents time. But a good number of students will complete all the questions correctly. So there are students who score more than 90% for this. Yes, this term all the exams will be online, including your Sunday exam, class test. All right, so all the exams will be online. So, and mechanics of there is no problem. Eva, you can choose either top or bottom. It doesn't matter. You can choose either top as compression or the bottom as tension, vice versa. So it doesn't matter. Both Dicheng and Heva. So one easy way is that always choose the top as compression, the bottom as tension. Either way, your answer will be the same because you're calculating the total force acting on the cross section to 0. So it doesn't matter whether the top is tension or the bottom is tension. Is that clear? Any other questions? Any other doubts? The residual stress also it becomes the same thing. So when you choose other than, so now for example, what you see here is this is chosen as compression because the arrows are shown in the opposite side and this is tension. So when you choose the other way, then you have to redraw the arrow directions, and similarly your calculations will slightly change. So if you want to do blindly, you can always choose, means as I'm showing you, you can always choose the top as compression. Correct, because this is how the stresses will be acting on the cross section. Okay, when a when a section is subjected to a movement, let us say a movement is acting on this. Okay, so if this movement causes the upper fibers as tension, okay, so the bottom fibers will be under compression. Okay, so the cross section may just look like this. Okay, with respect to the neutral axis, okay, so you can see here there is a compression and there is elongation here. Is that clear, Dichen? Eva, yeah. All right, so we move on to the next question. Okay, so this is a simple question. You can easily work on this. So here the yield stress is given 250 megapascals. Okay, so here the axis is given along x-axis. Okay, so all the dimensions are there. Okay, you're asked only to calculate the plastic moment and the maximum elastic moment. Okay, so what is the plastic moment and what is the elastic moment? Okay, so you can choose here the cross section. So okay, so here we are choosing this as tension. So this is the neutral axis we are assuming. Okay, so the top zone is compression zone 1. Okay, here this cross section is C2, the bottom is T1. Okay, so to calculate C1, C2, so we need to say that the resultant force acting on the cross section is 0. Okay, so C1 plus C2 minus T1 is equal to 0. So then establish this Y. Okay, calculate this Y. Then you'll be able to find out what is the compressive force in the upper rectangle. So what is the compressive force in the middle rectangle here, this portion, and what is the tension acting in the bottom rectangle with reference to the neutral axis. Okay, so you can establish Y. So you know the absolute values after that. So once you know the absolute values, then you can calculate the plastic movement and elastic movement. Okay, and for elastic movement, you need to calculate the moment of inertia. And yeah, the same formulas as you have done. So here there is no need for you to draw the residual stress distribution. No need to calculate the residual stresses. Okay, so this is simple and straightforward question. So you're just calculating only the plastic moment and elastic moment. So you were calculating what is T1, so you calculated what is C1 and C2, then the plastic moment, you can just apply this formula. Okay. So then you need to calculate inertia through the neutral axis for calculating the elastic limit. Okay. So for elastic moment, you can apply the formula, then just calculate. Guys, is that clear? Any questions or anything? If you want me to repeat, I can repeat. So we'll have a break around 8:30. So let me know any questions. After the break, I think I'll go through the what type of class test questions you can get. Uh, yeah, anyhow, I'm recording. So I'll stop the recording now. So any other questions, let me know. So the procedure is very systematic. I'm telling you that if you know the procedure and if you know how to use your calculator in a very fast way, then actually you can do all the calculations very fast, and you still complete the entire paper in 2.5 hours. And there are only two questions which will take a substantial amount of time in calculations. And one of the question is this calculating the plastic movement and elastic movements. Okay, so there will be other questions where the calculations will be simpler. All right, any other questions? And incidentally, I think your assignment questions are very similar or the same. Total number of questions for midterm. Yes, there will be only two questions, Darrell. Only two questions. I'll go through the type of questions after the break. So what type of questions this? Again, the good thing in solid mechanics is most of the questions will be based on your assignments. So only we'll be changing the numbers. Okay, otherwise the questions will be the same. Is that clear? Uh, yeah, any doubt, any question? Anyone, any questions, let me know before we break. After the break, I'll go through the class test questions and we can work out together. So you guys have no questions, then we'll have a break and we'll meet again. So 8:45. So let's meet at 8:45, okay? Guys, all right, Jakaria. How about other people? All right. So I'll see you all at 8:45. Hi guys, hope you're all back. How about others? All right, some more. All right, okay. So for the class test on Sunday, so you will be doing online and there will be two questions. Now, the first question may be something like this. So you may start working on this. So the three-dimensional state of stress is shown and you're asked to do a lot of calculations here. So the first part is calculate the characteristic equation and determine the principal stresses. And the second question, calculate the absolute maximum shear stress, then hydrostatic stress and the deviated stress invariance, calculate the principal stresses. Okay, so a lot of questions are given. So the first question, you have to do the characteristic equation. So characteristic equation, so you know what is the characteristic equation, right? So it involves the three invariants. Okay, so the characteristic equation is sigma cube minus I1 sigma square plus I2 sigma minus I3 is equal to 0. So, guys, can you calculate the three stress invariants for this? So, calculate the three stress invariants. So, the first invariant, okay, the answers are very brief. So, I think I'll use the screen. Okay, let me note down. Let me note down the. I think all of you please note down the stress tensor. So it is given as 100, 0, 0, 0, negative 240, then negative 300, 0, minus 300, and 320 megapascals. All right, so the Young's modulus is given 70 gigapascals, and the Poisson's ratio is given 0.25. You can see the screen, right? Or you can't see anything? Oh, writing I'll show. Because I myself was copying from there. All right, so sigma is, this is what is given. Okay, so this is given. So the first part is, what is the characteristic equation? I'll use, so to calculate the characteristic equation, so you need to calculate what is I1, I2, the second invariant, and the third invariant. So I3 is just the determinant value. So I1 value is simply sigma x plus sigma y plus sigma z. So can someone calculate and tell me how much is this? Any answer for this? 660 megapascals, that's correct. Then calculate I2. So I2 is two determinants, 100, 0, 0, 240 plus like 240, negative 300, negative 300, 320 plus 100, 0, 0, 320. Okay, so calculate I2 and let me know. 4.28 into 10 power minus 8. Any other answers, guys? Okay, calculate I3 and also tell me. So anybody to confirm the answers? So Faruddin is giving 297. No, the calculations you're multiplying with 10 power 6 into 10 power 6. So you will end up having 10 power 12. So for here you will have 10 power 18. So your answer will be much bigger, Shafaruddin. Because your answer differs from Deechen's answer. Anybody else? Any other answers? Okay, Heilong is giving 42,800 megapascal square. That is unit is correct. All right. So I'll confirm the answers. Zakaria is giving that should be megapascal cube, right? Okay, so your I2 is, as you can see, is 42,800 megapascal square. So your I2 is 42,800 megapascal square. So your I3 is, of course, I think you're giving the correct answer, negative 132 double zero, four zeros megapascal cube. Okay, so then you can write your characteristic equation of state of stress. Okay, so this is sigma q. Okay, so sigma q minus I1 sigma square. I1, so you just replace with 660. So I1 sigma square plus I2 sigma. I2 you replace 42,800. I2 sigma minus I3 is equal to 0. So this is your characteristic equation. So that means you must write your characteristic equation like this. So this way you are writing the first aspect I1 in megapascals, I2 in megapascal square, and I3 you are writing in megapascal cube. Okay, so this is the characteristic for the given state of stress. Okay, if you solve this equation, then you will get the three principal stresses. So guys, the next part is you need to solve the equation and find out whether your calculations are correct or not. Okay, so you need to solve the quadratic equation, solve the cubic equation, sorry. All right, guys, I started recording the session now. So once you solve the cubic equation, then you will get the three roots, and the three roots will be your solution. Yes, for the exam, you need to show the step by step. For the cubic equation, at least you need to identify which one is sigma 1. Yeah. So identify the three roots, then identify which one is sigma 1, sigma 2, sigma 3. So if you are using the traditional method, RSTQ method, then you have to show all the calculations. Is that clear, DJ? But can you confirm? No, there is no need to use the RSTQ method. You can still use your calculator to solve this, but when you use the calculators, you may not get the three roots in this format. Okay, sigma 1 represents the maximum value among the three roots. So sigma 3 represents the minimum value among the three roots. So you need to identify sigma 1, sigma 2, and sigma 3. Is that clear, Li Cheng? All right. So Can you confirm whether you're getting the similar values? I'm not too sure how many of you have the cubic equation. Of course, you can also use an online calculator to solve this. But many calculators you can use straight away to find the answer. Guys, can you confirm the answers? Sigma 1, sigma 2, sigma 3? So you get negative negative 22.65, that's correct. 100, yeah, sigma 2, yeah. So once you get, then you need to identify the order. So which one is sigma 1, sigma 2, sigma 3? So I think, yeah, D Cheng's and Chong's, both answers are correct. All right, so once you get that means you answered the first part of the question. So the first part of the question is calculate the characteristic equation and determine the principal stresses for the three-dimensional state of stress. All right. So you know how to solve part A, then part B. So calculate the absolute maximum shear stress at the point. So the absolute maximum shear stress at the point will be, okay, part B is quite simple. So you can simply write the absolute maximum shear stress tau max as sigma 3 minus sigma 1 over 2. So find out the answer and let me know. So this will be your maximum shear stress. So sigma 3 minus sigma 1. Oh, I'm sorry. So it should be sigma 1 minus sigma 3. So the maximum minus minimum. So any answer, guys? Sigma 1 minus sigma 3. So sigma 1 is our maximum, sigma 3 is the minimum. So you can, so you can see this is 582.65 minus 22.65. So that you will get 560. So sorry. Or is this 302? 582.65 minus 22.65. So minus of minus, therefore it will be plus. So you will get 605.3, 65.3 over 2. So that means that D Cheng's answer is correct. So the maximum stress is, maximum shear stress is 302.65. So it is sigma 1 minus sigma 3 over 2. Okay, so this is part B. All right. So the next part of the question, let us see. So the next part of the question is calculating the hydrostatic stress and the deviatoric stresses. So part C is calculate the hydrostatic stress and the deviatoric. So stress invariant. So this one is important. So the deviatoric stress invariance. So to do this calculation, first, hydrostatic stress means the mean stress. Okay. So hydrostatic stress is the mean stress. So mean stress means sigma x plus sigma y plus sigma z over 3. So you can also write this as I1 over 3, the first invariant over 3. So that will give you the first invariant you calculated as 660. So 660 over 3, that gives you 220 megapascals. Okay, so this is the hydrostatic stress or the mean stress. The next portion is you need to calculate the deviatoric stress invariant. So that means you need to calculate this I1 dash, I2 dash, and I3 dash. Now to calculate this I1 dash, I2 dash, I3 dash, so you need to write the deviatoric stress tensor. Okay, so you need to write the deviatoric stress tensor. So deviatoric stress tensor, the first one is sigma x minus sigma m. So sigma x is given as 100 and sigma m is 220. So 100 minus 220, you get minus 120. So the other shear stresses we write as it is. So this one is sigma y minus sigma m. So sigma y minus sigma m. So sigma y given is 240. So 240 minus 220, that gives you 20. Okay. So the last one is the sigma z minus sigma m. So sigma z is given as 320. So 320 minus sigma m 220. So that gives you 100. So the remaining shear stresses we keep as it is. Okay. So we have only this one is negative 300 and this one is negative 300. So therefore, what is that we have done? So we have written the deviatoric stress tensor. So this is the deviatoric stress tensor, sigma dash. Right? So once you know deviatoric stress tensor, then you can calculate the deviatoric stress invariance. Okay, so you calculate the deviatoric stress invariance. So I1 dash means we can simply write so sigma x dash plus sigma y dash. So the three deviatoric stresses plus sigma z dash. And as a result, you should get 0. So if you're not getting 0 means your calculations are wrong. So negative 120 plus 20, that becomes negative 100. So negative 100 plus positive 100, so you will get 0. Okay, this is the second deviatoric invariant. Sorry, first deviatoric stress invariance. The second deviatoric invariant, I2 dash. So I2 dash, again, you will be using the same formula from the learning guide. So here, How I do? First, I take these two by two matrix. So negative 120, 0, then 0, then 20. So this is 2 by 2 plus. Then I take this matrix, 2 by 2 matrix. So 20, negative 300, then negative 300, 100. Okay, so the third one, we take this one, this one, this one, and this one. So negative 120, 0, 0, 100. So if you evaluate these 2 by 2 determinants, so you will get the second deviatric invariant. So please calculate and check whether you get this number or not. And the unit is important, it is megapascal square. Guys, let me know anything you are not clear. So I clear the first deviatric invariant. So you can multiply this 120 to 20. Then you multiply 20 to 100 minus. So you multiply this. Here you just multiply these two. Add up everything. Okay. So the final answer should be, so you're multiplying with megapascal to megapascal. So the unit will be megapascal square. Then you just treat them as simply the numbers with the sign. So minus 120 into 20 plus 20 into 100 minus, so this 300 into 300, then minus this 120 into 100. So if you add up everything, so you will get negative 102 400 megapascal square. So is that clear, guys? Could you confirm the answer? That's correct, Michael. Thank you. How about anybody else? All right, teaching. So then the third deviatric invariant will be, so simply evaluate the determinant. So evaluate the determinant means, so we can write that I3 dash is equal to, so the good thing is there are, in the first row, 2 zeros are there. So we can simply write the determinant as negative 120 multiplied by, so we take 20 minus 300, then minus 300, then 100. So evaluate this value. So you should be getting this number. So this is megapascal multiplied by megapascal square. Therefore, you get the unit is megapascal cube. So guys, can you confirm whether you get this number or not? So you multiply this negative, multiply these two numbers. All right, Shafaruddin confirms. Anybody else? All right, so I clear this. So any questions? So this is how we first hydrostatic stress means the mean stress. Then we calculate the deviatoric stress tensor. So from the deviatoric stress tensor, we write this stress tensor. Then we calculate the first deviatoric stress tensor, the second deviatoric stress tensor, and the third deviatoric stress tensor. So whatever may be the stress distribution given to you, I1 dash will be always 0. Okay. So then let us go back to the next question. So the next question is calculate the principal strains at the point. So the part D is you are asked to convert the stress tensor into strain tensor. So you have to calculate the stress tensor into strain tensor. So guys, how do you do this part D? So you're asked to find the principal strains. Yeah, you can apply the stress strain relationship. So we can write, uh, okay, I'll just write here epsilon 1 can be written as, so because we are dealing with elastic relationships, Young's modulus is given and the Poisson's ratio is given. So the strain can be given as the principal strain 1 or 1 over Young's modulus, then sigma 1 minus Poisson's ratio into sigma 2 plus sigma 3. So if you, because we already know the three principal stresses from part A. So from part A, we know sigma 1, sigma 2, sigma 3. So therefore, you can use those values and calculate epsilon 1, epsilon 2, epsilon 3. So similarly, the second principal strain epsilon 2 will be, just follow this equation. So 1 over Young's modulus into here sigma 2 minus nu, the Poisson's ratio into sigma 1 plus sigma 3. Okay, so use these equations and calculate and let me know your answers. So once you calculate, let me know your answers. So I'll be waiting for your answer. Okay. What about the other values? Epsilon 2? Yeah, epsilon 1 is correct. So in the class test, you need to show all the calculations for this. So you can't give the direct answer. Huh? So you need to write the each equation, then you need to show all the numbers, then you give the final answer. And yeah, for online exam, please don't share your working with others. So what is happening is that, the same error carries in many um assignments or class test papers. So you can, if you want, you can share the final answers, but don't share the detailed working with others. So that way, everybody will get lose marks. There's a high probability. All right. So what about the second principal strain, epsilon 2? Anyone can confirm this answer? One minute, Heva. You're asking question D is not asking to find the minimum maximum strain, similar to question E. No, you are finding the three principal strains. Okay, so the sum of these three principal strains, you will be zero. You will be getting zero. So here automatically they will be in different order. So you cannot say which one is maximum, which one is minimum, but you can just give the three principal strains. So you can verify your calculation. You need to see that the sum of these three values you must get 0. Okay, Daryl says the first epsilon 2, right? Okay. Doesn't matter which is epsilon 1, epsilon 2. So you can write epsilon 2 because you are just following the equation here. So we are just following the equation. So calculate as per this equation. What are the three principal strains? Okay, so epsilon 2 will be 8.047 into 10 power minus 3. What about epsilon 3? Are you guys still calculating? All right, so I think Michael is saying all the three things are correct. Okay, so this is how you can convert the principal stresses into principal strain. So you have now the principal strain tensor. So your principal strain tensor will be, so it will be, so negative 5.714, so multiplied by 10 power minus 4, then 0 and 0. So here you'll have 0, then the second value will be 8.047 into 10 power minus 3. You can just follow the same matrix, Michael. So because you're just calculating, yeah. So the third row will be 0, 0, then negative 2.716. That means your calculations differ from the ones shown here. Never mind. You can just calculate now This will be your principal strain tensor. Then let us see what is the next question. So the next question is asking you, sorry, okay. The next question asking you to calculate the characteristic equation for the three-dimensional state of strain. So you need to calculate the characteristic equation now for the strain. Okay, so the part one is for the stress. Now part E, you need to calculate the characteristic equation for the strain. So to do this characteristic equation for the state of strain, so now we know the strain values. We know the three principal strains. So calculate from the strain tensor. So what is the first invariant J1? So J1 will be your epsilon 1 plus epsilon 2 plus epsilon 3. Okay, so your J2 will be so you need to follow the same formula for the strain invariants J1, J2, epsilon 1, epsilon 2 plus, because we are writing this strain tensor, principal strain tensor, as simply so epsilon 1, 0, 0, then 0, epsilon 2, 0, then we are writing 0, 0, epsilon 3. Okay. So if you write generically, we can write the second strain invariant will be epsilon 1, epsilon 2 multiplied by epsilon 2, epsilon 3 plus epsilon 3, epsilon 1. Okay, so the J3, the third strain invariant will be, so simply this would be epsilon 1, epsilon 2, epsilon 3. So please calculate these three and check whether you get these values or not. So I'll wait for your confirmation. Yeah, it doesn't matter, Dichan, because you are dealing with principal strains, right? So your J1, J2, J3 will be still irrespective of E2, E3. I think you just follow your calculation. These things are okay, the model solutions given for this problem, but you can just follow. J1, J2, J3 will be always the same answers you get. So once you know J1, J2, J3, okay, then you can write your characteristic equation for the state of strain as epsilon cube. So minus J1 epsilon square. The question doesn't ask about that, you know. So there is no need to worry about the shear strain in XY because anyhow it is 0. Okay, epsilon 2 square minus okay plus J2 epsilon minus J3 is equal to 0. So this is the characteristic equation. So now incorporate the values of J1, J2, J3, then you can write the final equation. Okay, so this is the characteristic equation for the state of strain, for the principal strain. Any other questions, guys? Let me go back to the first question. Okay, so you were asked only characteristic equation for the three-dimensional state of strain. So to find J1, J2, J3, we need to find, there's no need. No, because we are dealing with the principal strains already. Okay, so if you see here, the question asks you the principal strains, right? So when you are using the principal strains, so the other shear strain components will be 0. So that's why we write the principal strain tensor like this. So the principal strain tensor will be, so this is the principal strain tensor. So all the other shear strains will be 0. So when you are using this principal strain tensor, so your characteristic, your epsilon, J1, J2, J3 will be just like this. If you are not using the principal strains, but if you are using epsilon X, epsilon Y, epsilon Z, then yeah, the situation is different. So when you use the strains in the three dimensions, okay, the calculations will be different. Is that clear, Dixon, Eva? All right, so the questions will be something like this, but may have one or two additional components. I'm not going through those additional components that will be for you to work out. Then I'll move on to the next question. Okay, so the first question will be something as we have done, but it won't be exactly like this. All right, so it won't be exactly like this, but most parts of the question will be like this, but you may also be asked to calculate other components like what is volumetric stress, then what is volumetric strain, then what is the deviatric strain. So there could be additional things related to this. Um, but if you can understand the logic which we have done for all these 5 questions, then you should be able to very easily answer the remaining questions. All right, so then we move on to the second part of the question. So the second question is related to the von Mises and Tresca-Field criterion. Okay, so this is also we have done for your assignment. First assignment, I think milestone B, we have similar questions. So let us see this question. A material is tested and under proportionally increasing state of stress. So this is how the sigma 1, sigma 2, sigma 3 are related. So the yielding was observed when sigma 3 is 300 megapascals. Now you're asked to assume the von Mises yield criterion, and what would be the yield stress of this material under simple tensile loading. So you need to find out what is the yield stress sigma y. So when the material undergoes a stress relationships like this, and the sigma 3 values is given. So you need to just calculate sigma 3. Okay, so then the second part of the question is if the same material is used under the conditions such that, so here the conditions are changed, okay, but the material is used the same material. So that means you can use this yield stress from part A, then you calculate sigma 3, okay. So you can use the same yield stress value from part A, then you can calculate sigma 3. So again, these questions may be asked to use both von Mises criterion and also the Tresca-Yale criterion. Online. So the first thing first, okay, I clear these annotations, then start. So calculate what is sigma 1 and what is sigma 2, given sigma 3 is 300 megapascals. So what is sigma 1 value, guys? Anyone? So sigma 1 is 2 times sigma 3, and sigma 3 is 300 megapascals. So therefore sigma 1 will be, so sigma 1 is 2 times sigma 3. So sigma 3 is 300. Yeah, so sigma 1 will be 600 megapascals. So then what will be sigma 2? So sigma 2 will be 2 sigma 3 over 3. Or you can also write sigma 1 over 3. So what will be sigma 2? Anyone, guys, what is sigma 2? Yep, so 200 megapascals. So then use von Mises yield criterion. So von Mises yield criterion is sigma y is equal to, so 1 over root 2 . So sigma 1 minus sigma 2 whole square plus sigma 2 minus sigma 3 whole square so plus sigma 3 minus sigma 1 whole square. So you need to put square root for the entire thing. So I'll put to the power of half. So this is the von Mises yield criterion. So you may just calculate what is the yield stress. So guys, I'll wait for your answer. How to get 200 for sigma 2? Oh, no result. So it is given sigma 1 is 3 times sigma 2, right? So sigma 2 will be, so sigma 1 over 3. Is that clear? So Dicheng is giving stress as 360.6 megapascal. Anybody to confirm this value? So I'll wait for anybody to come out with a different answer or the same answer. I think the yield stress is correct. Your answer is correct, Dicheng. So this is part A. Guys, any doubts or any questions on this? So part A, any doubts or any questions, guys? Okay, Michael says no doubts. How about others? Oh, all right, Dicheng. So I have only get response from 4 or 5 consistently. So the remaining 25 students are silent. So it will be nice if others also respond. All right, Leander and Vinod. Okay. So let now focus on part B. So part B, the question says, if the same material is used under the conditions that, the part B conditions are 2 sigma 1 is equal to sigma 2 is equal to negative 3 sigma 3, and what value of yielding will occur sigma 3. So we need to find out sigma 3. Okay, so we use the same equation, the von Mises yield criterion, and we take sigma y as 360.6 megapascals. So we write 360.6 megapascals. So this one we write it as 1 over square root of 2. Then we need to find out sigma 3, right? So from this, we can write sigma 1 is equal to, okay, negative 3 by 2 sigma 3. Okay, so we can write this as probably minus 1.5 sigma 3. Then we can write sigma 2 is equal to, so we can just use as negative 3 times sigma 3. Okay, so now sigma 1 minus sigma 2, I'm sorry, I wrote here whole square, it should be whole square. Okay, sigma 1 minus sigma 2 whole square. So sigma 1, I write it as negative 1.5, sigma 3 minus sigma 2 wholes. Sigma 2 is minus 3.3 sigma 3. So minus of minus will be positive. So I write plus 3 sigma 3 whole square. Okay, plus then sigma 2. So sigma 2 is negative 3 sigma 3. So negative 3 sigma 3, then minus sigma 3. So I just write it as negative sigma 3 whole square plus, sorry, sigma 3 as it is, we write sigma 3 minus sigma 1. So sigma 1 is negative 1.5 sigma 3. So minus minus is positive. So we write plus 1.5 sigma 3 whole square and to the power of whole to the power of half. Okay, so we can relate the yield stress applying von Mises yield criterion in terms of sigma 3 like this. Now solve this equation and find out sigma 3 value. So in the class test, when you are doing this type of questions, so you need to provide step by step. Okay, if you just give the final answer, then you lose a portion of marks. So as far as possible, elaborate every step and logically give your final answer. Okay, you will have enough time. So time should not be a constraint. All right, please do the calculation and let me know your final answer. So So, guys, any answer? Heva is getting 103. How about others? So this is 22.25, 24.25, that is 24.5. Sigma 3 whole square. Reaching is getting 111.95. How about others? Let me get some more answers. So 103. Okay, so you can just try to work out this. So final answer will be, okay, plus or minus 103. So normally we don't bother about, I can say Dicheng answer is correct, Shafaruddin's answer is correct, and Hewa's answer is correct. Okay, so all these answers are okay, acceptable. Okay, but what's more important, to get full marks, all the steps must be given clearly. Okay, every step must be given. Uh, Guys, any questions? So this will be your second question. So please let me know if anything you want to ask. Anyone, any questions, any doubts, let me know. All right, Daryl says no. How about others? Then shall I clear all this? Safaruddin says no. I clear everything now. So basically, your two questions will be something similar. So please take note of the time when you are doing it. Okay, you need to upload your answer scripts before the day time. In the worst case scenario, if you can't upload, you can just immediately email to me, email to my Yahoo account, okay, uh, with a CC to Devaki. So you can CC me, okay, if you are unable to upload. I don't expect from anyone in the worst case scenario. So CC to Devaki. So you know Devaki's email, right? Devaki is the program manager. All right. So any other things you want to ask? The second question will be very similar to like this. The first question may have some minor variations, so there could be some additions to this question which I'm not discussing with you. Uh, all right. My sincere advice is uh, answer question one first. Answer question two first. Sorry. So sometimes in the past, what happened was that some students they start with question one and they may get some confusion and they may waste a lot of time. And by the time they try to attempt question two, they will not have enough time. So therefore, first you answer question two, then you go back to question one. Okay, so that way question two will be quite simple and be easy to answer. And in terms of weightage, the first question will have 60% weightage, and the second question will have 40% weightage. Okay, so always try to attempt question two first. Okay, don't spend much time on question two, maybe 20 minutes, then you go back to question one, then you can struggle yourself. So I think most of you can answer all the questions, and of course, as usual, there may be a problem for some students. All right, anything else you want to know? Please take note of the time. I think I'm not sure because Dr. Vivian was setting the time for evening, I think Sunday evening. Anyone notice the time? Please let me know. Yeah, so you will have 7:30 p.m. is the start time. I think the paper will be uploaded just 10 minutes before, so you can download the paper and then you need to upload the paper in 90 minutes. Okay, so if you cannot upload and if you send me, then if you can send within 5 minutes from your email, then there won't be any deduction of marks. But if the time is delayed, then the marks will be reduced. So for late penalties will apply. All right, guys, any other things? So the time is, please take note, everyone. So the time is evening, Sunday evening, 7:30 to 9 o'clock. Why all of you are silent? Michael says no, but Michael said earlier also. How about others? Teaching also no. Yeah. How about others? Yeah. Okay, Kailan. How about others? Okay, we know Safaruddin. So all these are familiar names. Daryl also familiar name. Okay, regarding class test, anyone has any other questions? Okay, so if you guys have no other questions, now the time is 10:10. So I will just go through. I think we have gone through this. So the next topic. Okay, so the next topic is about plastic design of beams. I'll not go through everything on this. So just to touch upon this, so this is plastic design of beam structures. So what happens when the materials are undergoing to plastic deformation? So sometimes it may be advantageous to have some amount of deformation into the structures. Okay, so those aspects we'll be discussing under this plastic deformation. Okay, so under plastic deformation, the important concept is uh, the plastic hinge. So we talk about what is known as plastic hinge. So generally, the plastic hinges are formed at points of load application at support locations. So whenever a structure is subjected to loads and it is undergoing plastic deformation, so these plastic hinges develop at support locations. Okay, we need to identify these plastic hinges. So, So what is plastic hinge? We can get to the concept. So where this plastic hinges forms at points of maximum moment. Okay. So plastic hinges will occur at points of maximum movement. We study the load acting when the material is undergoing plastic movement. So that limit load is called as plastic load. Okay, when the mechanism is undergoing plastic movement, so the load acting on the mechanism is plastic load. So, for example, you can see here. So a basic a beam, okay, so it is a roller supported at point C, so it is pin connected at point A, and a load of P is acting at let us say point B. Okay, so the distances are shown here. Okay, the load is located from point A at a distance of 3L over 4, and from B to C it is L by 4. So the total length of the beam is L. So in this case, due to the load which is acting at B, so there will be reactionary forces at both the ends, at A and C. So A and C will be the reactionary forces. So now we can apply the equations of equilibrium here, and we can find out, um, okay, the reactionary force here is P by 4, okay, by applying the equations of equilibrium. So we can identify the reactionary force at A, which is P over 4, and at reactionary force at C, which is 3P over 4. Okay. So when the load increases and the beam becomes, okay, the movements developed at A and C are plastic movements. So the load is termed as plastic load. Okay, so under plastic load, when the load increases, so the point B, okay, is the critical point. So at this point, a plastic hinge develops. Okay, at this point, the plastic hinge develops. So the plastic hinge refers to the point where it is subjected to maximum load. And these plastic hinges, okay, yeah, at points of maximum moment. All right, so I'll stop here. We'll continue in the next session. Now time is 10:15. Okay, let me know any other questions you have. So I'll capture your attendance for the last time. Okay, we have 32 students, all are present. All right, so guys, if you have no other questions, then you can log off. I'll be around to mark your attendance. Okay, so those students who want to ask any questions, they can stay back, others they can log off. Have a good night and